we want to determine the Young modulus for a beam, right? So I have a video which was shared by Vishal with me, and before I want to go to the video, I want to just give a little bit of introduction. What is it? So we all know about so basically when I say a beam, uh, it's a rectangular beam, something like this, okay? So it has a certain width and a certain thickness, right? My drawing is not very good, but I guess you understand what I mean. So it's like a scale, but it's a very long scale. So if I call this as my length, and this as my thickness, and this as my width, right? So you have 3 dimensions, so it's a 3-dimensional thing. And then what we are saying is we are trying to measure the Young's modulus, which I will define. So in any case, L is much larger than B and L is much larger than W, okay? And we can see this beam. So if you go to the lab, you can see it. So it's not a microscopic object. So you don't need a microscope to see it. So if we have such a beam, then what we are planning to do is we are planning to determine the Young's modulus for such a beam. What do we mean by that? So for that, we have to know something called Hooke's law. Okay, so Hooke's law is basically tells you that what is the stress and strain relationship. Within the elastic limit we are talking about. Okay, so basically it tells that stress is proportional to strain. Now these are quantities which I'm assuming that you know already, but since I'm just giving an introduction, I might just tell you. So basically, if we have such a relationship, then the constant of proportionality here, it's a kind of modulus, right? So if I call, you can call it whatever you like. Let's say I call it A. So we will define strain and stress, and there is a constant of proportionality, which is a modulus. And this is an elastic modulus. If we are within an elastic limit, what does that mean? It means that this is always proportional, linearly proportional to the strain. Okay, so stress and strain, if I call stress, if I denote this by, let's say, sigma, and if I denote this by, let's say, gamma, so sigma is A times gamma. But you might just think that, why it's sigma is proportional to gamma, but sigma could be proportional to gamma square or whatever power of gamma it could be, right? But we are saying that it is linearly proportional to gamma. That means the power of gamma is 1, okay? And that's an elastic limit. And in that elastic limit, this modulus is called elastic modulus. Okay. Now, so it is the ability of an object to deform such that, whatever strain you get, it's proportional to the stress. So let's see what are different kind of deformation you can get in general. So I'm sure all of you know this, right? So normally when you want to define stress, we define it force applied per unit area. This is how we define it. So we can have a deformation which could be linear, it could be angular, it could be linear, it could be angular, it could also be bulk, right? We'll see what does that mean. So what do we mean by linear deformation? Linear deformation, we mean that if we have an some object of some length L, let's say, and then if by somehow it changes its distance by a delta L, so it's a linear deformation, okay? By angular, we mean that if we have some object, let's say of this shape, and then I deform it such that it deforms and make an angular deformation. So something like this. So this is your deformation. This is an angular deformation of the object, right? Bulk means that if I have an object like this, and then it's the change is, so here the change is in angle, here the change in let's say length, here the change is in volume. Okay, so it has some pressure, at some pressure it has some volume. If I apply the pressure and if it changes its volume by delta V, so that's a bulk. So there can be three types of deformation. Similarly, you can have different stresses. So in this case, you have a stress. In this also case, you have, so this is called a tensile stress, if you like. So the stress corresponding to this is tensile stress, corresponding to this is called shear stress, and corresponding to this is called compressional stress. Okay, so these are some general concepts which are very useful no matter what area of physics you prefer or is your favorite. You will always encounter these terms. Now we come back to the Young's modulus. So Young's modulus is something that relates. So it's something like A here. So it relates tensile stress to the tensile strain. Okay. That is what we are going to measure for a beam. We'll see how we do that. So which means this is just force per unit area divided by change in length divided by length. This is how we define it, and we denote it by Y. So Young's is the name of a scientist who first thought about it. So you see, it's not a difficult thing. So, but I mean, maybe someday you will discover something, and then it will be on your name. So normally, this is how we. In physics, you often find the name of the scientist and some phenomena which is discovered, or some calculations, or some original work which is done by a scientist. It's named, it's given the name of the scientist who first discovered it. So this is very common phenomena. So we can measure it. So I think I will not go into angular and bulk because it's not relevant here. So I'll just stick to the Young's modulus. So what we have is, you can measure it, So in general, Young's modulus is a material property, okay? It's a material property. So it does not depend on the shape and size of the material. It's a material property. So what does that, it means? It means that if I have a beam, if I have a rectangular beam, or if I have a cylindrical wire of the same material, I should get the same Young's modulus for it. So normally there are two different methods you can measure. So one is called flexure method, and the other one is called Searle's method. Okay, so I think we are going to do the flexure method. So how do you, so let's just watch. But the condition here is that, as I told you, that the length is much larger than the breadth, length is much larger than the width. So, and also this ratio, so width by breadth, if you calculate this ratio, or you calculate, so there is a thickness of this, which I called, let me call it T, right? And then there is a width, which I call W, and there is a length. So these are the three dimensions. So you can take the ratio of this. And in any case, this is the condition which is always satisfied, okay? So what is the experiment? Let's just talk about the experiment, which I will show you the video now in a moment. So what is the experiment? Experiment is that we take a rectangular beam, okay? So we have a rectangular beam. It's a three-dimensional object, right? And then it is placed on something, on a table, okay? And then it has a distance or length. It has certain extension length, and there is no force applied on it at the moment. And then what you do is that you you in the middle point, you will see in the video that at the middle you have a place where you can apply load. So you have a hook kind of thing, and you can, you know, apply load. You can increase the weight here. You can apply weight, and everybody knows that if you apply weight on anything, what will happen? There is a force of gravity, right? That acts downward. So it acts downward in the minus z direction. So you have a force of gravity, so you can exert, so you apply a force on this, and then the beam will deflect. So let's say if I draw the beam like, if I draw a beam like this, right? Then if I start to apply weight, it will start deflecting, right? In the middle, of course. So let's say this is the middle point. And then as you apply more and more weight, it will deflect more and more. So what does that means? What does this deflection means? Or this depression? What is this depression mean? So if you now calculate this depression, this is what we want to calculate as we change the mass. So this is, let's say, 0 mass. There's no depression, and then you start getting non-zero depression, right? Or change in length. You see a particular change in length. And then if you measure this deflection or depression, right, you can calculate the Young's modulus. We can do this calculation, but normally the dependence of this is G is the gravitational constant, and this is 4B d cube m by L. So this is the dependence, and so this is where L is the change in the length, the depression that you produce. Capital L is the length of the bar or the beam. M is the mass that you apply. And D is, there is D and then there is B. So B is the ratio between width divided by breadth. And this is depth divided by thickness. Okay, and L is just the length. So this is what you have. Now we will see, so any experiment you do, I'm sure that by now you have done many experiments, and then like first thing is, to, so we are collecting the data, and then there are errors in the experiment. So you have to basically take the measurement and make a table. So we will also see how can we do this experiment and make the table. So let's just watch the video. What is the experiment? And I'm just sharing the one I got from Vishal. So I didn't make this video. Vishal sent it to me, so I'll just play it.
Hello everyone. So this is the experimental setup of the determining the Young's modulus of the rectangle using the rectangular beam. So you can see here the setup. So let's first focus on this rod. So this is a rectangular beam, you can see here. So it has a finite breadth. So we will try to measure it using the vernier caliper here. You can see here. And again, it has a very small width. So we will find this width using the screw gauge. So coming to the next part. So what we will do, we will put the, this rectangular beam on the two knife edge support. You can see here, first one, and here is the second one. So, and we will put it symmetrically so that the portion beyond these wedges would be same across to both the wedges. And then, and we will calculate this length between these two edge support, and we'll put this hook, as you can see here, at the center of this beam. You can see here. So if you note here, so this hook has a tip here. So here it has a tip at the top, and then there's a hook for the putting the weight on this. And now what we will do, we will use, as you can see here, we have a microscope, and we'll first of all try to focus on the tip of this microscope. So here we have already focused this microscope at the tip of this hook. So you can see here, so this microscope have a horizontal scale and a vertical scale. And yeah, so you can see here. So here is the vertical scale, and which will change by just rotating this top knob. So now here we have adjusted uh, the microscope. So you can see here. Yeah. Yeah, you can see here. Yeah, you can see here. So inside the microscope, there is a cross wire, and this wire we have adjusted just at the bottom of the tip. So this particular arrangement have a particular position, which is here on the vertical scale, and we will note this vertical position here. Then the next step would be to put the load over this hook. So as you can see here, we will put the load here. So we have some weights here, which are around of some are 500 grams, some are 400 grams, and we'll put these weights over here. So you can see here, we are loading this weight here over the hook. Yeah. So after loading this weight here, so you can see the position of tip on microscope will be shifted from its initial position. Yeah, you can see here. So now the cross is not touching the bottom of the this tip. So what we will do, we will we will rotate this knob, and so that we will adjust the tip of this hook to the cross of the wire. So after in this way, and we will note down the reading here on this vertical scale. So basically, so the difference in the previous vertical scale reading and this one vertical scale reading will give us the depression, and so that would be depression, and here is the weight, and we will repeat this procedure same by putting the other weights here. So you can see here, we will put other weights here. Yeah, and again, we will check the vertical scale reading over the microscope, and in this way, we would get a reading of the depression versus the weight. So we will make a plot of this depression against the weight, and well, from there we have a formula in the manual, and we will calculate the youngest modulus. That's it. Thank you.
Okay, so if you have any questions, you can ask me. Otherwise, we go back to the whiteboard.
Can you explain the crosswire part once?
Okay.
Where is it set?
Yeah. So basically, okay, let me just say to you. So,
and
the microscope part is not very clear.
yeah, so the question is, why do we need a microscope? It's a very good question. So the microscope is, so basically, okay, let me just draw something for you, okay, and then it will be. So why do we need a microscope at all? It's a very good question. Why do we need a microscope, right? So let me stop sharing. So what is a microscope anyway? I mean, why do we need a microscope? I mean, this is just measuring the young modulus. We have a beam, we can see the length, we can measure the breadth and the width. Why at all we need a microscope? That's the question. And what is the cross mark? So basically, you need a microscope to see something which you cannot measure very accurately with your eye. So if I have a length, let's say a scale length, and then if it changes by centimeter or millimeter or meter, you can see it. But if it changes by a very small amount, and if you want to see this kind of deflections, right, then how do you do it? So what we do is we take a microscope, and then there is an objective of the microscope, right? So every microscope has an objective. So it has a numerical aperture. It's a lens, basically. If you have done any optical physics lenses, and I don't know if you have studied it in high school, then you know that image will form. So there is an object, you can see you can use the objective to focus on an object, and it will form an image at the eyepiece, right? So in a microscope you have something called eyepiece, you have something called objective, and this is to focus an object which you have difficulty in seeing through naked eye, right? So the crosswire is just something that, if you, let's say this is your field of view that you see through the objective, meaning your eye. So our eye is also a kind of lens, right? So in the microscope, this is our lens, and we put our eye here. So basically, let's say I'm sitting here in the microscope, and then I'm seeing here, this is my eyepiece, and then in the microscope there is then objective, and there is a sample, and basically I'm putting my eyes in the eyepiece, and I'm seeing these small deflections. Okay, so I am using my lens, which is my eye, without the microscope, but since it's a very small depression and I cannot see it by eye very carefully, so I use eyepiece of the microscope, which is forming an image through the objective for the depression that is happening. And crosswire will help you to locate the let's say the tip. So there was also an image of the tip. So basically you put it at the center, because imagine that you're seeing something in the eyepiece, right? So let's say you're seeing something in the eyepiece, which in this case is the tip that you have to see, because this is what is by measuring the deflection of the tip, you can measure this depression. So if you want to see that tip, which has a very sharp point, you need a microscope to see it, because it's difficult to see it very carefully by the eye. Now the tip can be here, it can be here, it can be here, it can be here, anywhere, but the best way to put it is at the center. So what the crosswire does is, it tells you where is the center, and then you just focus it somewhere here. That's all, nothing more than that. So I think Vishal also send me a picture of the crossfire, and let me just go back and show you how does it look, and then you can probably agree with me. So let me share it. So this is a picture I got from Vishal, and you see this is the tip, and this is your crosswire. It just tells you approximately where is the center in the field of view, right? So this is the tip, and this you are seeing in the microscope. It would have been best if we have a scale bar here, which is telling what is the scale here, but we don't have. I'm sure you can find it out in the lab. So there must be some scale, micron scale, that you can put it in the microscope, and then you can measure. And basically this tip is going to move, okay? And then you are trying to find the deflection, like how much distance it has moved up or down. So one thing is that you can apply the masses, you can attach the masses, but you can also remove the masses, right? So when we do such experiments and we want to find the Young modulus, that it involves some length scales, it's always a good idea to not only increase it, but also decrease it. Then you get more readings, you get more statistics, and you can minimize the error, right? So the way I will do it is I'll tell you how I will do it, and then you can find your own way, and hope you agree with what I'm telling you. Okay, so now you saw the experiment, you saw the video, you saw where you apply the masses, and this was rested on a pin here, right? And a pin here, basically, so that there is no other contact points. It's a very small contact point, and basically whatever mass you're applying, you're applying on the beam, and you assume that it's it's uniformly distributed, because this is also consists of many small units, right? And if you're applying something here, you assume that all it is isotropic and uniformly depression and so on. It's not just this part, but it's a homogeneous material, and whatever you apply here, it basically tells you what is going on in the whole beam, right? But then we need to see this depression, and that we are trying to see by focusing a tip. And to see the tip, we need a microscope, and we focus the crosshair at the center of the crosshair, we bring the tip and then we try to see the depression. Okay, that's how we do it. And then you can change the masses. So basically, you know how you're changing the masses. That is something you put in. You know G, you know L. So then the variables here, actually B and D are also kind of you have to measure. You have to measure L, B, and D. This is what you have to measure to find L. Okay, so how do you so what you do is you go to the lab, right? You go to the lab and then you make a table. You make a table, something like this. So you have a vernier scale, you have a screw gauge, and that is for measuring. One case you want to measure the B, other case you want to measure the D. So you use the vernier scale and the screw gauge for that. But I'll make a table if I'm doing the experiment. I leave it to you what you want to do. But I mean, to me, this is what I will do. So I will write number of observations, the number of readings I'm doing. Right, and this is for first thing I will do is to measure, let's say, B, right? Similarly, the second thing I will do is to measure D. Okay, so I will make this kind of columns, and then I'm using a vernier scale, so there will be a main scale, and then there will be a vernier scale. So I will write, let's say 1, 2, 3, and so on. So I will write how much it is. Let's say this will be in centimeter, right? And what is my reading on the vernier scale? I don't know. You have, when you do it, you can find out what you get. So something like this, I'll make some readings in this direction, and then I will have the final reading from this, let's say in this case. So it will be final reading for B, right, in centimeter. So what will be in this case? In this case 2.60, in this case 2.59, and so on. You can write it. And then what I will do, I will take an average, right? It's always good to take a lot of statistic, and then you can get an average. Same thing I'll do for D, okay? So I'll make the same kind of columns, but now for this I'm using a screw gauge, right? That's the only difference. But I'll make a table now again. And then I will write again number of observations. Then I will have a main scale. Then this is number of divisions in the circular scale. And I'm just assuming that you are acquainted with vernier scale and the screw gauge. This is, I'm just assuming. And then you have a final reading. Let's say millimeter, and then you always take a mean. Okay, so let's say I have 1, 2, 3, so on. And the more readings you take, the better mean you get, and it's good for the experiment to get a better value of. So you always have to define something called least count. You have to define a least count for both. So typically this is what you have to calculate it, a least count for the, let's say for the screw gauge, and for here also you have to get for the vernier scale also you have to find out what is your least error. You have to calculate that for in both the cases. So and then once you have done that, so how do we define? Maybe you already know this, but maybe I just write it. So for the slide calipers, it's always good to know these things. So we define something like this, which is 1 smallest mean scale division divided by number of vernier scale division. So, and then for screw gauge, you can define wrist count. This is pitch of the screw divided by number of division. In the circular scale. So we always have to find this out because this will tells you something very important about the error. Okay, so this you have to find out, which I assume you know how to find it out, right? And once you have all this, then you make a table, like I said, and you get the mean value of the B and the D, right? And then you make a final table. When you have done that, you make a final table. And then you can also change the length. If you have different scales, you can also change the length. I don't know what you have here, what possibility you have in the lab. So you can have L, you can have a number of observations. Then this is the mass that you apply. You have to know the units. Then here is the reading in the microscope. Maybe I use a black one. Or the blue one. So now you have microscope reading. So I will do it both for increasing and decreasing load, but I leave it to you what Vishal tells you and what do you want to do. But if I were you, I will definitely do it for increasing and decreasing load. So this is increasing load. So I have main, vernier, and final. This is increasing load. Then I'll do it for a decreasing load. Main, vernier. Okay. I'll make a table like this.
Can you please explain what is increasing load and decreasing load?
So you apply, you add mass, right? So if you add mass, only then the depression will happen, right? Because we need a change in length divided by the length. So we need to measure what is the change, and we are going to connect that with this deflection, right? So this deflection will only happen if you if you apply the masses. So you remember in the video, let's go back to the video. So you remember, I hope you can see this video. So you remember this video that he is not just adding the masses here, but you can add it one by one, and then you can, so let's say I add first and the second and the third. So that's like increasing load or increasing mass. And then I can also remove one by one, right? So then basically I'm taking more readings and I'm collecting more statistic that will actually minimize your error. That's all I mean by increasing and decreasing mass, nothing more than that. Is this okay?
So basically you add a particular mass and then measure, and then you remove that particular mass and then again measure.
No, so what I will do is I will start adding. So let's say here in the hook, I'll start adding, right? So I'll, where is it? Yeah, so here. So I will start adding the mass here. I will not add and remove, but I'll start adding. So I will add one, then I will add second, then I will add third. So I'm making reading every time I'm adding. For the first one, I'm making reading. For the second one, I'm making reading. For the third one, I will making reading. Now, when again, what I will do now, I'm not done with my experiment. So what I suggest you do, and you can see a difference if you do it or if you don't do it. But I suggest that you just give it a try and see what happens. If you put one load, take a reading, second load, take a reading, third load, take a reading. And if you have more load, you can keep on adding and take readings. And then don't remove them all and don't call it a day. Then what you do, you take out one load. Now you remove it one at a time and then again take a reading. Then remove the second one, again take a reading. Then remove the third one, again take a reading and see. Because see, if you think about it, it's exactly the same what you did in the beginning when you were adding. So basically you were adding one and then you're removing one. So basically you think that you're doing the same thing, but just give it a try and see if you get the same reading. Okay. So why we are doing this? We are doing this because, let me go back to the whiteboard. So what did I tell you? Okay, so what did I tell you? I tell you that we are in the elastic limit, right? So what does that mean? It means that now you know force per unit area you're applying. You can measure the strain by looking at the depression. So strain is, in this case, delta L by L, and this is force per unit area. So you know what is the tensile stress you are applying and the corresponding tensile strain. The reason I suggest you do this, because if you now plot, if you plot, you will get a straight line, right? And if, let's say, I plot stress, I mean, this is not what you're plotting, but let me tell you that this is what I tell you, right? The Hooke's law, that it's linear, which means if you measure the slope at any point, that will give you the Young's modulus, right? Change in this divided by change in this. That's how you measure the Young's modulus, and it's the same because the response is linear. Now, what happens in the experiment, if you want to be an experimentalist anytime and you like to do experiments, then you may notice that what happens that if I'm increasing the stress here, I go from this point to this point, let's say I go from A, I go to B, and then I go to C, I'm increasing the stress, and I'm measuring corresponding strain. Now, what will happen if I'm decreasing the stress? So if I go from now D to C, C to B, B to A, do I follow back the same line? Or you can see that the more you go to more complicated system, for example, if you take a cell, for example, or if you take, I don't know, if you take what other thing, let's say a rubber band, okay, or you take some other material which is non-elastic, which doesn't have an elastic response, but there are materials which can change like this. Okay, there are material which can so beyond a certain stress, the strain is enormous, but the strain is hardly changing. So you can have material like this, you can have material like this. Okay, you can have material like this, that no matter how much stress you apply, there is absolutely no strain, but then suddenly it goes like this. Okay, so you can have different kind of response. So there are materials which are called elastic, and there are material which are non-elastic. Okay, there are material which are viscous and elastic, so viscoelastic, and soft material, like we are made up of cells, right? Cells in our body. And cells, if you want to see the response of the cell, if you apply a stress and what is the response, the cells are mostly viscoelastic. Okay, and I actually study soft materials. So most of the soft materials include, for example, it includes all the polymers, surfactants, and we are all made up of these materials. In our body, in the cell, we have polymers like proteins. So proteins are a kind of polymers, nucleotides are a kind of polymers, right? Like DNA, RNA, they are all polymers, nucleotides. Then you also have sugar, polysaccharides, those are also polymers. Maybe the spelling is saccharides. I have to check the spelling. So then you have surfactants like lipids, oil, you know, the oil that you use in the food. You can check all these things. So the response of all this material to the stress is non-linear. It's not linear. So if you do this experiment and see what will happen, not just when you increase the load, but what will happen if you decrease the load, that will confirm you the response that it is elastic and linear. You know, sometimes it happens that if I go from A to D, I don't go from A to B to C to D, I go from A to D, or if I just come from D to B, then whether it follows the same trend or not, you can check that. So that's why I think it's a good idea. If I were you, I will do like this, right?
Excuse me, ma'am. The reading in microscope would be small l.
So what is the small l? Let's see what's the small l.
And also, what is the
depression.
depth and thickness?
Yes, so say it again.
And what is the depth and thickness?
What is the depth and thickness? So
Yes, ma'am. Of which object we are calculating here, ma'am?
for the beam, the deflection is happening for the beam, right? There was a beam in the video, right, which is deflecting. So
Yes,
you are
ma'am.
creating by adding the masses here.
Yes, ma'am.
You are increasing the stress by applying the masses due to the gravity. The more the masses, the more force you will apply, the more depression you will get.
Ma'am,
Yes.
Ma'am, I'm
Ma'am, I
talking
have
about
a
depth.
doubt.
ma'am, can
deep.
you explain how the depression is calculated using the microscope? How we calculate the scale?
Yes, I can explain. Let me finish this. I'll come back to that. So then you have main rating. Let me finish this table. And then you can get the depression. So you get L1 and L2. And then basically you have both L1 and L2. Right? If you want, you can also take an average of these two. So whatever the final, so let's say I have one kind of length, I don't know, let's say 70 centimeter. And then I make few observations. And then the masses I have, let's say 0, I mean half a kg. I don't know what masses you have. You can do this. Then you can have this reading for all of this. So all this reading, and then you go from 0 to half. Then you could also you can also go back and you know, not just increasing, but you can also go back and you can have this. So maybe when you go from 0 to half, I don't know what in what steps you can go in the lab, because the video, I have to watch the video again. You can basically take the average of this plus this here, right? And then for calculating the depression, so when you have no mass, let's say you get a value A1 here and B1 here. So the final reading will be A1 plus B1 by 2. And this is for 0 depression because you have no mass. So this will tell you a little bit. So you should get a 0 value here. So the depression we are calculating is L minus the new change. So this is delta L is L final minus L original. This is what I'm calling depression. So with no mass, you will have 0, but as you increase the mass, you will increase it. So I don't know, you have to check it, what you get, and then you will have some values here. So I'll make a table like this. And I will tell you how to use the microscope and all. And then once I have done that, then I'll go back and I will make a plot. Now, so I will plot here depression. So plot here depression, which is L, and this, let's say this is in centimeter, and then I will see how it is for different length of the beam. So this is for one length, this is for another length. So if you could change this, I should get these lines, and on the x-axis, so I'm just plotting this versus,
The
sorry,
mass which we used.
yes. So, but I'm yeah. So in this case, this is, so let's say 0.5. So you can plot this, okay? And then you expect the straight line. Why you expect that straight line? Because if you now go back to this, this M versus L is what you're plotting. M versus L is what you're plotting to get Y, which is, if you say that this is not changing, right? Because this is something to do with the beam that you have taken. What you are changing is you're changing M, and the corresponding L you're measuring, which is same as delta L. You're not changing capital L, you're not changing B and D, which is related to the length, the width, and the thickness. So once you have a given beam of a given length, it has a certain thickness, which you are not changing. It has a certain width, which you are not changing. It has a certain length, which you are not changing. So this whole term here, it's a constant, this thing. This is a constant. So basically I can write it. I can write Y equal to constant times M by L. And then if I plot M versus L, so L versus M, if I plot, and then you get a straight line, because this is a constant, and the slope of the line, if you like, depends on, I mean, in this case, probably L. So M is Y times L, right? And of course, there is a constant, some constant here. So if you, from this plot, by measuring the slope, so this will be 1 by Y. So by measuring the slope, you can calculate Y. This is the whole idea.
Excuse me, ma'am.
Yes.
Ma'am, B is the ratio of width by breadth, that is W by T. So ma'am, in the table where we are measuring B, we are using vernier caliper. So the observation and reading of vernier caliper, so it will only give the width, na? Then how are we calculating the T?
How are we calculating the?
And the breadth.
No, so I define B as the ratio, which is width and breadth. So width, you know, and you can measure, yes.
Width and breadth would be the same thing, like it is written slash for that reason, maybe.
Yes, ma'am. Are you using thickness and width as interchangeably? Because depth and thickness, like.
Yes, I am using it interchangeably, but I'm saying that, yeah, actually you are right. I'm using it interchangeably, but what I mean is you basically have just these three parameters, L, T, and W. You don't have anything else, right? Is that okay? I mean, if you have a B, you know these three things, right?
Can you please define B once again? Is it a ratio between width and breadth or just width?
No, so I was defining it as a ratio, but like one of you pointed out that it's the same thing, right? But what I was saying is that one thing is you can see it with the eye, but when you use a vernier scale, right? When you use a vernier scale and you want to measure, let's say we want to measure the, what is this, W. So L we can measure easily. We want to measure W and we want to measure T. These are the two things. For W, we are using vernier scale. And for T, we are using screw gauge. Okay, so I mean, this is almost, it should be one. So now I think it's a valid question, that what am I taking in this formula? Am I taking a ratio, or if I'm taking a absolute value? And I think you have a good point. So thanks for that. So in the formula, I'm not taking the ratio. So here I said this because, you can, so it should be close to 1. But in the formula, you cannot take 1, right? So you are right, absolutely right. And thanks for this. So when you have this constant, then for B, so thickness is T and width is W, right? So you have to have W, and this is going to be thickness. So it's not the ratio in the formula, it's the absolute value. Is this okay?
Yes, ma'am.
So instead of B, you can also, I mean, you don't have to calculate the ratio, you can, like what you mean, you will see, like if you see any differences, right? And what is the variation, that's what I mean, but you don't have to. So you can just take directly, because then otherwise there's a confusion, what do we have it in the formula? So I guess that's fine if you take just this. Any other question you have?
Ma'am, the reading from the vertical scale of the microscope, it is same as like that of calculating from any vernier caliper. Like we need to calculate it in.
Yes. So you have to calculate it in, say it again.
I was saying that it is the same way like we do for any normal
Yes.
like object using a vernier caliper.
Yes, it's the same way. Yes. Yes. Yes, it's the same way.
And
Excuse me, ma'am.
Yes.
Ma'am, why haven't we included the mass of beam in our calculations?
Yes, very good question. Why we haven't calculated the mass of the beam? And the reason I said to you that, you assume that the mass is equally distributed, and basically if the thickness is very small compared to the length, you say that, the mass of the beam is very, very less, and it doesn't play a role. But I think you have a very valid point why we are not using. So we are ignoring the mass of the beam, and we are saying that basically that, you have something which is, it's like a essential like a wire, and then you are just deflecting the wire by applying a mass, and these masses are much larger than the mass of the beam, and you can ignore the mass of the beam. But you're right. I mean, it's a good question.
And maybe the simplest thing you can think of is like that, because what we are seeing is how the depression is happening based on the difference of the masses. That's what matters for us. Okay, so you can ignore it. That I would say first.
Yeah. So when you have this plot, this is the M which you apply, the mass that you apply, and this is the deflection. And your question was that if we are also changing the scale, we are changing the L. Basically, if we have L1 not equal to L2, then basically it could be that they have different masses. And your question was that why we are not taking that into account. So it's a good question. But and also I want you to go back and think that, is it true that the mass is homogeneously distributed? It could be that, that there is a mass distribution which is very non-homogeneous. But you can always make something more complicated. You can go on and do that, right? But this is a very simple experiment, and we are trying to simplify it. So we are not considering the mass of the beam. And also this for a given scale, as Vishal says, that if you don't change the scale, and if it's for a given scale, and you are applying these masses, then the mass of the beam, again in the linear regime, you assume that, whatever changes happen, because I changed something here. I mean, this was the point I started the lecture, that you change something here, but then you are assuming that response as the response of the beam. And that is only true in certain cases if you assume that, the response is equally distributed. And then the density will matter, like how the mass is distributed. So you are just ignoring those complicated things and you're saying that, okay, this is a beam which very less mass, and whatever masses you're applying, you're changing, it is uniformly distributed over the beam. There is no heterogeneous mass distribution, and then you can safely ignore it. So the response of the beam to the stress that you apply, it's linear. And we are assuming this, and then we are calculating the Young's modulus with that. Is this okay? So Vishal, what I have to do with the assignment, can you help me with that?
Okay, so so I think we the video and maybe the slides you have prepared, so we can upload that one and then they will submit. So what we found that they have a problem with this Moodle. So I'm using now this Google Classroom actually to upload.
So maybe you can tell me what to do, and then I'll just do that.
Okay, yeah. So maybe you can send me the slides and the video. So I will upload them, and then I think that will be okay. So
sure.
And I will share with you the rights actually also.
Yeah, okay, sure. So is this okay? Can we stop it here?
Yeah, I think you have a class also, right?
Yeah, I postponed my class, so it's okay. I thought it will be too much to start a class at 10.
Okay.
Yeah, tell me.
How are we doing error calculation in this?
Have you done error calculation when you tried to use vernier calipers and all that? Did you do that already?
That would be least count error.
Yes. So you have to calculate that in the beginning. That's why I said that you have to calculate. And if you really want to go, actually, there is also, actually, again, it's a very good question. And I simply can't stop explaining this because all of you are asking very good questions. So let me say something about the error analysis also. So I had a class from 10, but I postponed that. So I have time, all the time for you. Ask me whatever you want to ask. So it's a very good question. Error analysis. So one is the list count that you do it anyway, right? And then how do I determine? So what I have Y. I mean, maybe these symbols are different in your manual. So, I mean, I leave it to you which symbol you use. Just use the one you like. Which one is your favorite? What will be the error in Y? Tell me. Have you done this in your high school? I'm sure you have done this. So how do you calculate the error in Y? I'm writing, just check if you're fine with this. So 4 is just a constant, right? Or maybe I write it. And then we can take it as a constant. Did I miss anything? GL cube. Again, I wrote B. W4 T cube ML. So this is your total error. Now, this is going to be 0. Okay, this is going to be 0. This is going to be 0. Right? And this is going to be 0. Right?
Ma'am?
Yes?
Ma'am, are we measuring the length of the beam by meter scale?
Yeah, so normally that is given to you. So capital L is the total length, and that's something given to you. So that is long. Let's say it's 70 centimeter or 90 centimeters. So that you can measure by the scale. I mean, that you can see, right? Now W and T, they will be in centimeter and millimeter. So that's a little bit, you can make error. So that's why we use vernier caliper. We use like vernier scale and the screw gauge. Yeah. So it depends on what we are measuring, but length of this and the scale is given to you. You can see how big it is. So that's not a problem. So this will be your total error in Y, which is delta Y. You can calculate this as one of you asked me. And then if you want to calculate this thing, this is going to be, if you, so something like this. I assume that all of you know this. So this is how you do calculate the total error. It's called transmission of error or propagation of error. Error. In an equation like this, you can write it like this. And this is again a very general concept. You must go back and read error analysis and how the error is propagated from one parameter to other. So what we get is, what do we get here? So this L square and there is an L cube here, right? Something like this. Now I told you that you do it in an increasing load and a decreasing load, and the L, then you can, then total del L that you have, if you take an average, you can take it delta L1 plus delta L2, right? So you basically minimize the error in Y. The more statistic you have, you minimize the error in Y in that case. So this is what you get. And then, once you know the L, you can calculate your delta Y by Y if you know. So L is something which is given to you, right? Let's say 70 or whatever centimeter. Then thickness also is given to you, something. And then you also know the least count. L you can take from the graph for a given L, right? And then like that, you do it, let's say for 3 different L. So you have 3 different values of this L1, L2, and L3. Okay, and then take an average of that. And then you can find out this. So this will give you the error in Y. And let's say you get some value of this. So if you get some value of this, so what will be your delta Y? You can calculate Y times whatever value you get here. You can calculate, and then when you want to write now Y, so the value that you calculate plus minus delta Y, this will be your answer in whatever units you are taking. Is this clear?
And what is the delta small l? What is the least count of that scale in microscope? It's the same as vernier caliper.
No, this is the depression. So this is the
Yeah. So what will be the error in measuring the depression?
Yes. So if you go back to the table, this table, and you have these L values here, right?
Yeah.
So I said that we take one as L1 and one as L2, right? And then basically you can calculate here, you can calculate what is the mean L1 and what is the error or the what do you call deviation, standard deviation.
Okay.
L1. Similarly, you can calculate here mean L2. I mean, I'm just increasing the number of error calculation that you have to do, but you just by doing all that, you are actually minimizing a lot of error. So, I mean, this is the proper way of doing it. I mean, you can also do you can try different things. You can do it without it and then do it with this and see how your values changes. So it will give you some taste of what are the error in the system. Is this okay?
Yes, ma'am.
Okay, very good. So are there any other question or should we stop it here?
So maybe I will just say something, because actually what you're doing, you have can you go, because you have this formula, right? If you say this equal to y equal to mx, actually, because you're changing m and you're getting a depression, from there you can get a slope, and from there you can just you can think of this as kind of assume for a constant. Then you from a slope you can get a y, and also because you are getting a different values, right? Because with the and then from the slope or error on the slope also you can get error on the young models. That's also one way roughly you can do. And but you will be getting a slope error, but then you have again the error, and as Dr. Bhatia has explained to her, that the error propagation. So there are few other ways actually you can play around. Okay. And the data you will be getting will only have the like one reading. It's not like putting the weights, it's not like unloading. So from there you can directly get this one. Okay.
I wanted to ask that for the previous experiment, we used a different formula for the propagation for error. It was like a root mean square formula for the propagation.
This is a fxx2. That's the most, this kind of a general one. That's like, this is kind of an approximate, like with no correlation taken into account. The one which you did for the error propagation with the like partial derivative, that's actually taking the correlation, and that's much more like I think like general formula which you can implement anywhere. Okay, that's the difference.
Okay.
Okay.
So should we stop it here if there are no more questions? Or so the video is shared with everyone or it's only with me? Vishal?
No, video is not shared with everyone. So, but now I will put on that one. So I will share on the Google.
No,
okay.
So should I show it? Do I need to show it again or is it okay?
No, I think because it's already here, so it will be uploaded so they can see later.
Okay.
So within like 1 hour, it will be uploaded. So
Thank you, ma'am.
Also,
could you put it on Google Classroom, like on Moodle? It's often a
so
problem.
now I'm putting on the Google Classroom everything. Okay.
Okay,
Now
sir.
Moodle is working maybe.
Yeah, so maybe all that you can discuss with Vishal, and then I just wait for an email from Vishal, and then I just upload it. I just send everything to him, and then you can decide with him how do you want to have it and how it should be uploaded, if that is okay.
I wanted to ask that you did not tell us anything about the readings. Like, what are the readings that you gave us?
What readings?
So it's actually okay. So the readings are the same, like as I think Dr. Bhatia has mentioned. So what you need the length. The length is actually on the depression, on like how far it is, that is there. And then you have the thickness, you have the width, and the depression is also there, but it's only for the loading part. Depression is there. Okay.
Yes,
Using
sir.
that, you
So,
can do one.
So will you provide us the observation
not.
table?
Yes, it will be provided. I think that's let me, I think I did shared. Okay, so this is actually let me,
should I stop sharing? Or?
Yes, if you can, I think that would be, yeah. So okay, so these are the tables, like this is the mass and this is the kind of okay. So you have initial tip movement, final weight, like what is the depression. So with the mass, with the weight, and you have a depression. Okay. So you have this information and you have this G1, the information here. So this will be provided to you. Okay. So I will share this Excel sheet. So from there you can do. Okay.
Yes, sir.
Okay. That's from. Okay, so I will share this in the Google Classroom.
So one more question. The vertical knob was there to adjust the focus at the tip of the tip which we were viewing. Is it correct?
So first thing is as Dr. Bhatti has explained. So you focus first on the tip, right? Once it's focused, it stay there, right? You don't really have to change. What happens is when you're putting the weight, actually, it's going down, right? That's what you are trying to see, that how if I put this much, how much faster it bend or slower it bend, or how much weight. That's what you are doing with that. That's the simplest thing I can explain. So when you put, what do you expect? The tip to go down, and because it's
Yes,
an
sir.
inverted one, so you expect it to go opposite, right?
Yes, sir.
Okay, that's what you see, right? And so what you do is you actually try to do is you just because it's actually changing the middle wire, the cross wire, which you're saying this is kind of an arrow, right? So I just focus on the middle point. So when it changes, what I do is I just move my microscope, right? Which is we call it traveling vernier caliper or something, you can say. The moment it moves, what you are seeing is how much the distance it moves actually, right?
Okay, sir.
That's exactly
Thank
what
you.
you're doing. Okay. Okay, simply I'm just checking the how much is bending. That's why we call depression. That's it. It's the simplest thing I can say.
Excuse me, sir.
Yes.
So what kind of error estimation will be doing for the flywheel experiment? The standard deviation, because
Yeah,
the
I think
error
standard
propagation
deviation
one
will
will
be
very
standard
easy.
deviation will be easier. Okay, just do that part. Okay. Because
Okay.
you will be
Okay,
getting
sir.
few measurements you have, so from there you estimate. That's okay. Okay, so any questions for Dr. Bhatia? So if not, thanks, Dr. Bhatia,
Yeah,
for
thanks.
explaining nice experiment.
So I'll stop the recording now.
Yes, yes.